Okay, so what we're going to be looking at today, we're going to be taking a look at gears and the features of a gear, your common spur gear. Your spur gear is your gear with a little bit larger tooth. If you can use your imagination and bear with my drawings, the ones that look something like this. I just do the intersection because I'm not talented enough to draw the full gear without really making it look ugly. But some features that we want to know about these gears. Of course, you have the depth of the tooth, which is that full distance there. But these gears don't penetrate all the way in. The tip of this tooth is not going to come in and touch the inside of that. That's what we would call the inside diameter of your gear. It's actually that point there to the base of the tooth, that blue circle. And then there's something called an outside diameter, which is all the way out to the edge of that tooth. And you can see that the outside diameters of the gears mesh, they intersect. The inside diameters, of course, have quite a bit of clearance. And the outside diameter of one will not quite touch the inside diameter of the other. Well, somewhere in between there, if I can draw a picture here of the teeth. Yeah, I know they don't curve much. As we said, the tooth of one gear does not, penetrate all the way in and touch the inside diameter here of the other gear. But if you look at the gears overlapping, there is a point that is halfway between the outside diameter of one gear. The outside diameter of this gear on the left is there. The gear on the right has an outside diameter there. There's a point exactly between the intersection of those two outside diameters. And that is, for both gears, one would wrap around this way, one would wrap around the other. That is called the pitch diameter of the gear. That's very important because that's basically the working circle of the gears where that pitch diameter is at. That's the amount of space that the gear, that's the unique space that gear occupies. Outside of that is the space of the gear next to it. It's also very important because that's the diameter, that circle formed by that diameter is the circle that we consider the spacing of the teeth of that gear. We talked a little bit about this before when we were talking about ratios, how the teeth of a gear have to be exactly the same spacing, exactly the same size, or they're not going to mesh with each other. Well, the term that describes that is called pitch. Pitch describes how far apart two teeth are on a gear. There's something called circular pitch, which is actually probably the most easy one to understand. And the circular pitch uses the pitch diameter. The pitch diameter is usually labeled as just D. Good morning. So when we see D or diameter, we're referring to that pitch diameter because that is the diameter that most defines the circle, or the circle that most defines that gear. This pitch circumference then is just going to be pi times that pitch diameter. That's going to be the circumference around that pitch circle. So then the circular pitch itself is that pitch diameter divided by n. Now, we've used n before for RPMs. In this case, n is the number of teeth on the gear. So if you think about that, pi times d, that is the diameter, or the circumference of that circle, the distance around that pitch circle. If we divide that up by the number of teeth, what we get is the distance between teeth at that pitch circle. That's the spacing of the teeth. Remember, so that's the working diameter or working circle of the gear. That's the point where that spacing has to be equal for those gears to mesh. That's actually also the point when the gears are pushing on each other. One gear is going to touch. Let's say the gear on the right here is the driving gear. So that's also the point where the most force is going to be applied from one gear to the next, one tooth of one gear to the tooth of the next, to transfer that force and that motion from one gear to the other, is at that pitch diameter, that pitch circle. So that is the circular pitch. Now, because we have to do pi times diameter and divided by the number of teeth, it's a little more work. So we have some simpler things we're going to look at. But let's do an example of that for right now. Let's take a gear that has a pitch diameter of 3.25 inches. And this gear has 16 teeth. So the circular pitch will be pi times 3.25 over 16. So when we do this one, since there's only one number on bottom, remember we talked about this a little bit, if there's more than one number on bottom, we have to use parentheses. But here there's only one number down here, so we don't have to worry about it. It's just going to be pi, or 3.14 we'll use. I think the packet uses 3.1416, just a little bit more accurate. So we'll do 16 times 3.25 divided by 16. What'd you get? 0.64. Perfect. The eraser didn't write so. So you have a pitch of 0.64. So that's telling us is approximately points, and that actually is in inches. So it's about 0.64 inches, a little over 5/8 of an inch between teeth. Now, because of the fact that that was, pi was involved in that calculation and all that, we tend not to use the circular pitch much. We tend to use something called just the pitch, or sometimes referred to as the diametric pitch. We've talked about this before as well when we talked about pulleys and pulley ratios. Since the circumference is just the diameter times pi, we can use the diameter in place of the circumference in calculations, and just knowing that we're off by that pi factor. So our diametric pitch, P, is defined as just the number of teeth divided by the diameter. Now that seems backwards. It seems like it should be diameter divided by the number of teeth, but that's just the way they calculate it. So what that is instead of giving inches between teeth, it's giving us teeth per inch. So let's say that we have that 16-tooth gear again with the 3.25 inch diameter. That is giving us 4.92 teeth per inch. That's what that's telling us. These are the two basic formulas for dealing with spur gears. If you guys have your packets from yesterday, if you'll pull those out for me quick. I'll pause this, give you a second to dig them out. Start recording. So you see on that table, starting page 247, going to 248, there are a ton of different dimensions that we're going to be looking at here. If I go back up to my picture, working depth, that describes the distance from, that's just the distance between those outside diameters of the gears. It's how far the teeth actually penetrate or overlap each other from one gear into the next. So here, let me get some of my mess out of the way here. The working depth on this one would be from here to here. That's how far the teeth actually penetrate or overlap each other. Technically, it's how far the outside diameters of the circle overlap. Things called the addendum, the dedendum, that is just the distance from the pitch circle out to, if I can find a usable color here, pitch circle out to the end of the tooth. So let me put my pitch circle in here. So that's my pitch diameter for this gear on the left. Excuse me. The addendum is from the pitch circle out to the tooth. The dedendum is from the inner diameter out to that pitch circle. So basically, they're just the difference between the inner diameter and the pitch diameter, and then the pitch diameter to the outer diameter on each of those gears. It also, though, describes, if we look at page 248, for standard gears, if we know those numbers, we can get to the pitch diameter, and all that stuff from them. You'll notice the bottom formulas, they're starting with the addendum and going down. Most of them have an asterisk by them. All your gears are defined by the degree, they don't have perfectly square teeth sticking out on them like this. The teeth come out and they're beveled. like that. So what that asterisk is telling you that is for a 14.5 degree involute gear. All that means is that's the bevel on the edge of that tooth is 14.5 degrees. Very common. That's the most common one when you're dealing with spur gears. So I'd say probably 80% of your spur gears are going to fall in that category. Just be aware of it that these are not geometric. They're not come from the basic geometry of a circle if they have that asterisk by it. They do come a little bit from the geometry of a circle, but also then the geometry that's assumed with that 14.5 degree bevel on that tooth. So anyway, let's say that we are given that we have a gear with a working depth of 0.425 inches. And we want to find what is the pitch of that gear. Why would you ever need to do something like this? Well, let's say you're looking at the strength of the material in your gear and you know the amount of force that's going to be transferred. The working depth, remember, describes how far these teeth are going to be overlapping. So it describes how much surface right here is going to be in contact from one tooth to the next. So that'll tell you how much force can be transferred depending on the strength of material those gears are made out of. How much force can be transferred from one gear to the other, because you're looking at pounds per square inch. That working depth combined with the thickness of the gear, the width of the gear, however you want to describe that, gives you the surface areas in contact. And then you can use that to calculate PSI and see if you're within the specs for that particular material. So let's try to find, now that we know that we need this particular working depth for whatever metal we're using in our gear, figure out what pitch gear that's going to be. So if we look, if we look at pitch, there's nothing in the pitch that relates to the working depth, which is always our first option. If we're looking for pitch, you look at your formulas for pitch. But in pitch, we see pitch is related to diameter, it's related to circular pitch, it's related to the number of teeth. That's all we have in the pitch formulas. So then we try to go backwards. We look at what we're given, the formulas for what we're given, and see if we can work backwards to the pitch. So let's look at the formulas for working depth. If we work there, we see that there are formulas there for working depth. One relates to the circular pitch, one relates to the addendum and the diameter. But there's also one that relates to, the addendum and dodendum. There's one that relates to pitch. So up there it says working depth, WD, is equal to 2.157 divided by the pitch. Now again, there's an asterisk there, so remember that is for your standard 14.5 inch or 14.5 degree bevel. So in this case, we know the working depth. So I'll put in our 0.425 for the working depth. This one's a little bit tricky because the value we're looking for is in the denominator of a fraction. We have a couple of options. We could multiply by p to get out of the denominator, but a trick that I'm going to show you that's going to be used over and over again in trigonometry in a couple of weeks. If the value you're looking for is on the bottom of a fraction, turn this thing into proportion. So now we're looking for this value here. We're just going to cross multiply 1 times 2.157 divided by 0.425. So 2.157 divided by 0.425. What's that? Did I do the whole depth instead of the working depth? Oh, I'm sorry. Thank you. Good catch. Yeah, for working depth. Wow. Well, good catch. Thank you. Working depth is WD, isn't it? It's 2.00 over pitch. How many of you caught that? Just were afraid to tell me. A couple of you? Okay.
Is that 2,000 or
2.00? That's what that is. So our working depth of 0.425 over 1, again, we're going to make it a proportion, just like we were trying to do before. So it is 2 divided by 0.425. .706, it looks like. So probably call that a 4.71 pitch. is where you'd end up. So anyway, now we know what the pitch of our gear, that's, again, pitch is saying number of teeth per inch. So that's a relatively fine-toothed gear. We might run into problems where the solution isn't readily apparent. We'll run into some where we have to maybe go through a couple of different levels. We might be given let's say that we are told that we have 10 teeth and a pitch diameter of 2.5 and be asked to find the hole depth. So let's look up a formula for hole depth. The formula for hole depth, that's the WD, is, bless you. Well, we can either have the circular pitch, we have the pitch, or the addendum and dedendum. We have the 2.157 over the pitch, or we could have 0.6866 times the circular pitch. The addendum and dedendum, we're not even going to worry about that one. We don't have the pitch or the circular pitch. So we look at the other information we have. We have the number of teeth and the pitch diameter. So let's look at the pitch and circular pitch. Circular pitch, if you flip back to 247, well, you can find the circular pitch from N and D. If you look at just the regular pitch, you can also find the regular pitch from N and D. So in this case, we could use either formula. We could either use the pitch, we could find the pitch and use that to find the hole depth, or we could find the circular pitch and use that to find the hole depth. I am inherently lazy, so I'm going to look at the one that's the simplest. Circular pitch, remember, involves pi. Whenever I use pi, it's a little bit more of a messy calculation. So I'm going to use pitch. So I'm going to use this formula here. And I know that pitch is number of teeth divided by the pitch diameter. So here that'll be 10 divided by 2.50. Well, what's 10 divided by 2.5? 4. That gives me a nice round number to work with. So that's telling me now I can use that combined with my working depth formula, or hole depth formula here. 2.157 divided by 4. This 4 is my pitch. Perfect. 0.53925, 0.539 we'll call it. And that is in inches. That's our working depth. What do you guys think? I want to pick one out, have you guys give it a shot, see how it goes. We're looking on page 252. Actually, I want you guys to try 2 of these quick for me, and then I'll give you the homework. On page 252, I want you to try number 35 and number 39. So I'll pause this so you guys have a couple minutes. I'll give you a little more time for 39 in a second. Number 35, we're asked to find the dedendum. If you look on page 248 for the dedendum, there's 2 formulas for the dedendum. You either need to know the pitch or you need to know the circular pitch. Well, the information we're given in this problem is the number of teeth and the pitch diameter, which means we can find either one of those again. I'm going to find the pitch, because the pitch is simply the number of teeth divided by the pitch diameter. So for this one, we have 44 teeth and a 3.6667 inch pitch diameter. So we're given, that's going to round to a 12, a pitch of 12 for this gear. So now going back to the formulas for the dedendum, we know the dedendum is 1.157 over the pitch. So it'll be 1.157 over 12. Now you might be asking, where does the 1.157 come from? That again is a constant for any 14.5 degree bevel spur gear. So 1.157 divided by 12. 0.096. So that's the duodenum. Of course, that is in inches. How many of you got that one? Did you understand the logic of how to get to it? So for number 39, you're given pitch diameter and the pitch. You're looking for the root diameter. Well, if you have the root diameter, you need the pitch diameter, which we're given, but you also need the duodenum. So we got to figure out how to find the duodenum for the root diameter. So I'll give you some time for number 39, and we'll come back to it in just a second. So on number 39, finding the root diameter, we were given the pitch diameter, D. That's one of the things we need to know. The root diameter is the pitch diameter minus 2 times the duodenum. We don't know the duodenum. So if we look at the duodenum, for the duodenum, we need either the pitch or the circular pitch. Well, for number 39, we are given the pitch is 12. So that means the duodenum, D, once again, this 1.157 is a constant over 12. We already figured this one out to be 0.096. Figured that out, the exact problem out in the last problem. So the duodenum is 0.096 inches. We put that in here. So then our root diameter is 2.9167 minus 2 times 0.096, giving us 2.7247 inches. What do y'all think? Okay, well, we have about 25 minutes of work time here. I want to give you plenty of time to work on these. In this packet, it's going to be starting on page 251 through 252. We're going to be working on 1 through 53, the odds. I would highly recommend you do pretty much all of these. There will be a test coming up. This is a very short unit here. Your unit test will be coming up probably next Tuesday. Just so you know, tomorrow morning I will not be here. I have a doctor's appointment again tomorrow morning. Hopefully this is the last Thursday morning I'm gone for a while. But yes, prepare for a unit test on Tuesday. What's that?
I said we won't complain.
You won't complain? Oh, don't.